Comes on everyone. Let's start off. The last thing that we did was the breaking stress. So what we did so far, we were just playing with this equation here. First thing we defined something called stress, which is force perpendicular to the cross-sectional area, longitudinal stress. Right. So we are studying right now longitudinal stress and longitudinal strain. And what is longitudinal strain? Delta L by L. Then when you take the ratio of longitudinal stress by longitudinal strain, you get something called Young's modulus, which is phi. From there, we got this formula TL by AE. T is the tension, L is the natural length, A is the area of cross section, and E is the elongation. There, we are just playing with this one formula so far. So, last thing that we did was this sphere. Now, same thing, I can have a different version of this. Instead of having a sphere, what if you have a very long cylinder? We have a long cylinder, radius r. Long hollow cylinder with a very small thickness. T. R is much greater than T. Same story, right? And this long cylinder, right, is filled with gas. P is the pressure. Outside, you can take it as vacuum. B is the breaking stress of the material. Find maximum P so that the cylinder will not crack. Last class, I gave you a hemisphere, right? Sphere. Same thing. This thing I made a cylinder, a long cylinder. So you can ignore the edges ka effect actually. Find max pressure so that the shell doesn't crack. This is a good one. Hope you remember how we did last time. Last time we took a hemisphere, half shell. Then we drew an FBD, we found the tension, and we said tension by that cross-section area is the stress, and we equated it. Take a minute. Let's see how will you handle this. I hope the picture was clear. It's a long cylinder, so you can ignore the edges. It's an infinite cylinder, basically. Inside it is filled with gas. If you keep on increasing the pressure of the gas, at some point it will burst, meaning it would look something like this. Can you see how it opened? So you will get a crack like this. It will tear open. So how much is that pressure? BT by R, okay. Let's see. 2ST by R. What is S ray? Surface tension. This is elasticity. Surface tension chapter got over long back. Breaking stress. Let's see. I don't remember the answer actually. Take a minute more. I'll show you. BT by R, okay. So the most important thing, like how do you choose an element? That is the headache there. See, this is how we choose an element. I'll just try to draw a side view and then I'll show you there. Uh, so how you choose an element, actually you take a small slice here. Something, how do I draw this? Just 3D shapes now, I'm bad at it. If you have a cylinder like this, hmm, you basically, how do I draw this? Let's see, do I have a picture? Hmm, there, there. So when we have this shape, we will choose an element like this. So we are taking this line here, right? So we are taking a small strip like this, everyone. So there, this is your element now. We are taking a thin strip. This angle is d theta, and this is r. Able to visualize how is the strip? Meaning if you draw a line like this is d theta, and that is r. Are you able to visualize how is the strip? It's like this, a small hemisphere kind of thing. And how is the tension acting? The tension is acting parallel to the surface, kind of like surface tension only. The tension is acting like this. Now, if you see the side view, the front view basically, this is your tension. This is your tension. This thing we did in circular motion room, but 2t sine d theta by 2. This is d theta by 2. This is d theta by 2. So who is pushing it out? The pressure is pushing it out, which will be pressure of the gas into area. What will be the area of this strip? This length here is r d theta, and let the length be L, which is not given. So that will be area will be L r d theta. So from here we will get 2 times T. This angle will be d theta by 2. Sine d theta by 2 will be pressure into area L r d theta. For small angle, sine theta becomes theta. This will be 2t d theta by 2. That will be P into L r d theta. D theta will cancel. 2 also will cancel. We get tension will be pressure of the gas into L into R. Is this clear so far? So this is the tension acting on the thin strip on both the sides. It is stretching. Are you able to visualize how it is being stretched? Any doubts on this page? Please ask me. Now, what is stress? Stress is tension acting on the area. Which area? Now, if you look at that strip, it is not actually thin. It has thickness. It has some thickness like this. So the tension is acting on this thickness here, where this thickness is T and this length was L. And your tension was acting on this area. So the longitudinal stress will be tension by area, which is tension by L into T. This should be equal to the breaking stress. You don't want to break, right? So this should be less than equal to B. But what is the tension? PLR by LT must be less than equal to B. LL will cancel. We get P must be less than equal to BT by R. This is your maximum pressure. As long as you're less than this, you're safe. Anything more than this, the shell will crack. So be careful. Huh? What is this area here? This is the surface area you're getting at. RD theta is this area. Because when you take pressure into area, this is your surface area. But when you take stress, tension by area. This is cross-sectional area. So you have to be careful which areas you're talking about. All will look like areas only, but yeah. All clear with this? Yeah, decent question again, but yeah, if you see, this is a little bit of circular motion ka thing which we used. This is the third time you're seeing this concept. First time you saw in circular motion, second time you saw in surface tension. Any doubts on this? So that is the reason it took pretty long, because if it is not long, the problem hoga, the edges mein na, that it will become like a cylinder here, it becomes a problem to solve. So we don't want that edges to have, so it's long. L will cancel anyway. Any doubts on this? There, fluid mechanics, elasticity, two chapters we combined. A bit of circular motion ka that mathematical thing, 2D sine theta beta. Let's see one more. This is an easy one. We have a long rope. We have a rope of density rho. Area of cross section A. B is the breaking stress. Find the maximum length of the rope that you can hang so that it doesn't break. Gravity is there. This is a CET level question. So if you're hanging a rope from the ceiling, so this is a rope hanging from ceiling. Find max length of the rope that can be hanged without breaking. This is the issue that you actually face in lifts. When you have very tall buildings, right, like this Burj and all, 100 floors, right, you cannot have a single lift going from the ground floor to the 100th floor. You can make it, but it becomes very expensive and becomes very heavy because the weight of the wire which you're hanging becomes actually multiple times the weight of the lift. So if you ever been to Burj, right, the lifts, right, you have think you have 1 to 40, and then you have to get down and change the lift and go from 40 to 80 or 90. You have to change at least 2 to 3 lifts. So when you're going into skyscrapers, that is the thing. It's very inefficient to build one lift from 1 to 100. The weight of the wire just becomes too much. So people are thinking of a concept, to make a lift without wires using magnetic repulsion and attraction. There. So things are like that. If you're building a 20-floor building, it's not a big deal. But the taller the building, the problem is an issue. That lifts become actually an issue. How to do this thing? So why is the rope breaking? Rope is breaking because of its own weight. We will have some theoretical questions later on, Arya. So tell me one thing, which point on the wire will experience maximum stress? If you are doing a pull-up, right? If you're hanging onto a wall or something, which part of your body will feel maximum stress? Your hands or legs? Your hands, right? The topmost point, isn't it? So if you're hanging, the topmost point will experience the maximum tension because of the weight. So this point here, A, experiences maximum tension. So if you're safe there, then you're safe everywhere. So tension at A will be the total weight mg, which is nothing but density, area, length into g. So the stress will be tension by cross-sectional area, which is rho Lg. This must be less than equal to B so that you don't break. So L must be less than B by rho G. बस इतना ही था. Easy? So that entire weight of that rope will generate tension at the top, and that will try to break it up. Just have a look at this. Mhm. Yeah, next thing. Great. So we saw about this force and stuff. Actually, there are some really good questions based on thermal expansion, which we'll see in the next chapter. Next chapter will be thermal expansion. So next thing, now if you have forces, then you also have energy. Elastic potential energy. So consider a rod fixed at one end, and the other end is pulled by a force F. Till equilibrium. And let the elongation be E in equilibrium. So we have a rod you're fixing on the left end. Y is the Young's modulus, area, length L. Right? And initially, this is your natural length. Now you started applying force F. Now, when you apply force F, immediately, initially the tension will be zero because you're in natural length. Now, as you're pulling the rod will start getting stretched. Let this elongation be X. See, suddenly you won't reach equilibrium. So at this point, what will be the tension? We know from the formula Y is equal to tension length by A delta L. So your tension, if you see, this will be Y A by L into X. So your tension is not constant. So tension varies as you keep pulling. It's kind of like a spring, actually. We will see that. We'll compare this with a spring. Tension varies with X. And eventually you will reach an equilibrium state where the rod will stops. Technically speaking, the rod should keep oscillating, but let's say it has reached equilibrium. So this is your final elongation. At this point, the force F and the tension F becomes equal to T, which is YAE by L. This is in equilibrium. So remember that. So tension is not constant. It will keep increasing, increasing, and eventually it becomes constant. Now, work done by tension. Now remember, tension is your internal force. Will be minus because it is acting left side and the displacement is going to the right side, minus TdX. Now remember, the tension is not constant, so I can't say directly tension into length. I have to integrate this. This will go from 0 to E. This would be minus YAE square by 12. And we know work done by internal forces is equal to minus delta U. So from here you get the change in potential energy is equal to YAE square by 12. We can write this in a much better way. Let me show you that, but have a look at this. Now, so if I write this thing, elastic potential energy, so we got YA E square by 12. This can be written as half into FE, because if you remember that F will be, this is the final tension T final, which is equal to YAE by L. So I'm just replacing it. You can write like that. The elastic potential energy of Fe, you can also do this thing. You can divide by area, multiply by area, divide by length, and multiply by length. Then we know half F by A, that becomes stress. E by L becomes strain. A into L becomes volume. This is another way to write the formula of stress into strain into volume. I don't like this, but there's a much better way to write this. You can also write, if you remember, Young's modulus is equal to stress by strain. So I can write strain as stress by Young's modulus. So it will be half stress square by Young's modulus into volume. This is a better one actually. You will see later on why. So you can write like this also, elastic potential energy. And if you divide elastic potential energy by volume, there's a name for this. This is called energy density. Energy per unit volume is called energy density. They can ask you this in units and dimensions, which is half stress into strain. Basically, just remove the volume there. So that the whole thing is important actually. So you can remember any one, and from there you can modify the formula. You can do twist it however you want. But there's a problem with this. This formula, right, is under the assumption the final tension, if you see, is constant. So these formulas are valid only when the tension is constant. Because when you used F, that you're taking it as a final tension. Valid only when tension is same throughout the rod. So every point should have same tension. You should not have different tension at different points. Valid only when tension is same throughout the rod. If your tension is changing with position, you can't use these formulas. Okay, have a look at this. Clear how we derived this? We found the tension YAX by L. Because it is changing, we integrated, we got this YE square by L. Then we just kept on the formulas and modified them. There, this is your second formula. The first was the elongation thing, and the second was the energy. Now, by now, if you noticed it, right, you must have seen some resemblance. This thing, yeah, bolo.
Sir, the elastic potential energy वाला जो formula है, half stress into
Hmm.
strain into volume. I think
Yeah.
that will be valid for every element, right? Or it will not be.
Element है ना, element अलग है. We're not talking about element.
Okay, for the entire rod, it's not, but
We
for
are just
element it
taking a
is.
word. Why bola na? Tension is not same, then don't use this formula. Meaning we'll use this, but not in this form. All clear with this? Now, if you look at this, I'm sure you must have seen this. By now, you must have got a feeling like, it is kind of looking like spring. Actually, we get the spring formula from here only. If you compare this with a spring, look at this thing. So tension is equal to YA by L into E. You can clearly see this is looking like F is equal to KX. And if you look at your elastic potential energy, which is half into YA by L into E square, this looks like half K square. So that means when you have a rod YAL, you can replace this with a spring. whose spring constant is given by YA by L. Now, do you guys remember this formula? The spring constant, so K into L is Y into A. This was constant. Remember cutting of springs? So when you cut a spring, the lenses will change. So this we studied in NLM. There, if you remember, I wrote the formula here that time. K is equal to YA by L. Y is called Young's modulus. A is that area of cross section and length L. That time you didn't know all this. But if you, I hope you remember this formula though. We kept on using this though. K into L is constant. So this thing was from there, page 178, laws of motion. So I'll write it down here. You can refer. But again, same problem. You can convert the rods into springs only if the tension is constant. Because if you remember in LLM, all our springs are massless and they have same tension throughout. So whatever I taught you so far, you can use everything. If your tension is constant, just convert them into springs and you'll get your answers. Any doubts on this? Clear, na, Shreyansh? Tanishka? Clear with this? Advait? Got this? Anvita? Clear? Vedika? Got it? No. There is some heat produced actually here. Now, when you look at that scenario there, when we took the rod initially at the natural length, and then finally when the rod has become like this, in equilibrium, you have moved by a distance E and you're applying a constant force F. So work done by external force is force into displacement of point of application of force. Yeah? The work done by external force is simply force F into V. I don't care about tension. I don't care about anything else. It is force into the displacement of the point where you applied the force. And that point has moved distance E. But what is elastic potential energy? Half Fe. If you remember, we have done something similar in surface tension also. Even there, you lost half the energy. So what happened to the remaining energy? It has become heat. So this will be work done by external force minus elastic potential energy is half Fe. So whenever you stretch a rod, you actually lose energy there. So technically, what should have happened? Do you guys remember this question? When you take a block and a spring, and if you leave it, the block does not stop at the equilibrium position. Do you guys remember the problem? The block continues to oscillate. So technically speaking, if instead of a rod, if this had been a spring, and if you had applied force F, this block would have oscillated front and back. So technically speaking, that would have been kinetic energy. But since we said it comes to equilibrium, maybe due to internal forces, friction and all, so it all becomes heat. Are you clear with this? So logically speaking, it should have oscillated. And you can actually feel this also, if you have your pen car refill, if you take your pen car refill, right, and if you bend it and make it stretch, bend it, stretch it, bend it, stretch it, bend it, stretch it, do this pretty fast. And if you touch that point where you bend it, you will find it is hot. Have you tried? Yeah. But you should do it really fast, and you should bend it at the same spot multiple times. Like bend it, make it straight, bend it, make it straight. And if you do that, that point becomes really hot. There is a video on Versatinium channel. These NASA people, right? They have a material where when you actually bend the rod and you make it, the rod becomes really hot. So they actually use that as a material to make tires for the vehicles on moon ka surface. Because you can't use a regular rubber ka tires on moon ka surface. Moon ka surface is pretty rough and it will tear through it. It's like a sandpaper. So there is some material. I think, let me see if I can find the video. I'll show you the next time. So you can actually feel this thing whenever there's a deformation. So generally, whenever there's an accident or something, right? When if your car or train or something hits something, After that collision, inelastic collision, the body actually becomes really hot. So that is one. But here there is a theoretical question. This is important. What if you're applying force and very slowly if you're increasing? If F external is not constant, but it is slowly increased. This F is constant. Slowly increased, that is, the F external is always equal to the tension, which is always equal to YA x by L. Means you're applying little slight change. So then work done by external will also become half Fe. Then the energy stored also will become half Fe. In this case, there will be no heat. So this will be a theoretical question. So they'll give you two statements. A constant force F is applied on the rod and the rod reaches equilibrium. Find the heat produced. A force F is applied on the rod in such a way it is slightly slowly increasing. Then find the heat produced. Clear with this? So be careful with that note. That would be a good theoretical question. So if you're applying force always equal to slightly more, you will not have that oscillations. Any doubts on this? Great. So we have basically all the formulas, right? If you have uniform tension, this is important. Listen carefully here. So if your tension is constant, then your elongation is given by tension length by AY. Straightforward formula. Your elastic potential energy becomes half into stress square by Young's modulus into volume. This is the thing I prefer to use, but you can use other formulas also. So use these formulas if your tension is constant everywhere. Uniform tension. What to do if you have a variable tension? We integrate. But I know the formula only when the tension is constant. So what do we do? That is the whole point of integration. I know the formula for a rectangle. How do you find area under the curve? We take such a thin element, dx. Since dx is so small, I can assume tension is almost constant. That is the whole concept of integration. Now I can apply these formulas for the dx element, not the whole rod. We can assume tension is constant in dx. So the dx rod will stretch by a small amount dE. So dE is the elongation in dx. So length of the rod is dx and the elongation in the dx rod is dE. You're done. Apply the formulas. So what is the formula there? Elongation dE will be tension as function of x. Your tension is not constant. Into length ka place mein we have dx by ay. Therefore, your elongation will be integral T dx by ay. That's how formula modifies. And what about the energy? So elastic potential energy will be integral half stress. Stress is nothing but tension by area into volume, which is A into dx. There, everyone. This is how your formulas will modify in case the tension is changed. Instead of taking the whole length of the rod, we just take a dx and finish it off. Yeah, it's like a reversible process. That's what you do in that. All clear with this? Have a look at this. So last class when we did everything with constant. Now we are going to do when everything is variable. And again, there are not too many models, like one or two models, you understood them, everything will look same. Let's see a question. You can copy down in case you want, but yeah. Okay, let's see a question. We have a rod on a smooth surface. We have seen this in NLM. Mass M, length L, area Y, and you're applying force F. Find the elongation and the energy stored. Step one, find the tension. Step two, put in the formula and solve. Done. That's it. That's what I keep saying. If you know how to find tension, problem is over. Once you got the tension, you have to just dump it in this formula and integrate. But still, give it a try. I'll show you this one. I'll ask you one more like this. But first, you try for 1 or 2 minutes. Find the elongation in the rod and find the energy stored. Chalo, so everyone should try. Let me show you one. Listen carefully in case you have no idea. If you got it, others keep doing it. Step one, find the acceleration. F is equal to ma. Then you want to find the tension. What you do, wherever you want to find tension, cut it there. X. Then take any one piece. I'll take the front part. What are the forces? F, tension. The mass of this small piece will be m by L into x. Acceleration A. F minus t is equal to mass into acceleration. We get tension is equal to F into 1 minus x by there. So this is your tension as function of x. This you should know. Matlab, this thing came from like what? Newton's laws of motion. We have done this. Exact same question we have done. Here. There. Can you see? Exact same question. Great. Now what you're planning to do? So for this rod, you have taken a small piece dx. So in that small piece dx, the elongation is de. So I'm just doing the whole thing again. So you want to find elongation. So de will be tension. Length of the rod is dx by ay. So elongation will be integral. Tension is F into 1 minus x by L dx by ay. This goes from 0 to L. Fay is constant. That will be x minus x squared by 2L. You'll end up with FL by 2ay. And what about energy? Elastic potential energy is integral half into, now you'll understand why I took that stress, because stress is simply tension by area. Instead of finding strain, stress, and putting everything in the formula, this will keep your life easy. This will be half stress square by Young's modulus, and the volume is ADX. And what is the stress here? Stress is simply tension by area. So you can just substitute here. Half, that would be F square. by y, 1 minus x by L whole square. A also will come out here, dx, 0 to L. So this will be f square a by 2y integral. When you expand that, you'll get dx minus 2x dx by L plus x square dx by L. It's kind of integral. So we can integrate this. How much will that be? This thing will come out to be L. That will be L square by 2. LL will cancel. 2 will cancel. That also L. This is they will go off. That would be L cube by 3. That is L square. So we get f square by 3 will come out. F square a by 6 y L 6 6y. This is L square. I think we'll get something like this. F square L by wait, I messed up. This is a area square because stress, no? So A also will come in the denominator. F square by 2ay. We can integrate that. F square L by 6ay. Check. Right, Utsa. Right, Arya. Right, Samyak. Right, over here. All got this? That's an integration, x power n ka integration. You can handle that. I hope all clear with this. Let's see one more like this. I'll change it a bit. Same thing. We have mass m, area A, length L. You are applying 2f. You are applying f. X is equal to 0. X is equal to L. But the Young's modulus y is equal to y naught 1 plus x by L. Your Young's modulus is not constant. Can you just find the elongation? You can find the energy stored also. It will be just lengthy. For energy, you can just write the equation and leave it if you want. This is a variable Young's modulus. We have a rod whose Young's modulus is changing now. Tension is also changing, Young's modulus is also changing. Both are messed up. Find elongation in the rod. I think the integration will be messed up, I guess. रुको एक काम करते हैं change it like this. Put in the denominator. Better.
सर वो वाला अच्छा आता है।
है
आई गेस वो 1 + x/l कैंसिल हो जाता है।
नहीं कैंसिल नहीं होता इसमें. Tension is not 1 plus x by L. You can do it. Integration partial fractions करके integrate करना पड़ेगा. Max that you will handle it, but ठीक है. I'm not interested in the max part now. Get me the equations. I change the Young's modulus. Y naught by 1 plus x by L. Y naught is constant. Step 1, find the tension in the rod. You know how to make it more deadly? You can actually change the linear density. Lambda is equal to lambda naught x. Then that will become even more messed up. Okay, let's not get there. You can change a lot of things. You can make a rod of variable density, variable Young's modulus, variable tension. Try everyone. A little working is involved, but yeah, it's not tough. 7 FL by 3 AY, 13 FL by 6 AY. We have two different answers. So step one, let's find the tension. 2F, F, acceleration will be F by M, same as before. Cut it here at a distance X. Then take this piece. 2F, tension, acceleration. So M will be M by Lx. So 2F minus T is equal to M by Lx into acceleration. We get tension is F into 2 minus X by L. Yeah, check. Did you get the same tension? That's the first thing. If you goofed up here, then the whole thing goes for a toss. Great. Once you got this, elongation will be integral. The formula is still valid. Tension dx by ay. So your tension is F into 2 minus x by L. Area is area only. Y will be y naught into 1 plus x by L. That is the reason I brought everything in the numerator. If I had kept it like the previous one, you would have got 2 minus x by L by 1 plus x by L. You can solve this. You can add plus 1 and subtract 1. Then this guy becomes 3 minus of 1 plus x by L by 1 plus x by L. Could be done. 3 into 1 plus x by L minus 1. And then we integrate this. This will come a long term and this will come a normal x term. So it's not a tough integration, but okay. That's more of a math than the part. You're over actually. Okay, question. Integrate this, you'll get the answer. You want energy? Integral of stress square by Young's modulus into ADX. This will be half. That would be F square by A square 2 minus x by L whole square by y naught into 1 plus x by L into ADX. Again, it's just brute force. It's lengthy. You just have to expand and solve. Anyone got an answer here? 13 by 6. We have two answers. 2 by 3. 3 by 2. None of you got the same thing. I think two people got 13 by 6. Can you guys check whether you got the same thing? If you got the same equations, then we are done. Matlab, then you must have goofed up the calculations. Just multiply this. It's an x power n ka integration and finish it off. Yeah, 13 by 6. I think three people got it. So looks right. I'll leave it here. You can simplify and you can check out your own. 13 FL by 6 A by. Energy part, it's fine. You can leave it. But I hope you got the process right. You find the tension, put in the formula, you'll get the answers. There is nothing more on this thing. Even though it looks like something complex, this is how you keep doing. Stress is nothing but tension by area, and then you're done. Any doubts on this? Yeah. Now here there's a small shortcut, especially at a mains. Now you can use this. If you have a rod, and let's say if you have forces F1 and F2, right, and Y is constant, YAL. You can only do this for elongation. We can find something called tension average. Which is F1 plus F2 by 2. And we can get elongation, which is simply tension average L by AY. You get this kind of questions in main. Suppose if the forces are in the same direction, F1 and F2, then your average tension will change. Then your average tension will be F1 minus F2. Put in the formula, you'll get the answers. Valid only for elongation. Don't use it for energy, because for energy it is a square function. It's not a linear function. You can take always average when the functions are linear. If the tension is changing as x power 1, and only when tension varies linearly. You know the reason, right? Mathematically, because if you have a linear function, understand the meaning of it. I'll leave again in case you forgot. If you have a linear function, right? When you say I'm integrating, you're actually finding area under the curve. This thing forms a trapezium. So what are you doing exactly? H1, H2. If you remember the trapezium curve formula, half into H1 plus H2 into L. So basically, you're taking the average of these two heights. So you're taking this point as the height for everything, and you're just getting the area, isn't it? This works only for linear functions. Suppose if it is a curve like this, you can't do it. So whenever you have linear functions, you can take average and finish it off. It works. So just to give an example, suppose if you have a rod here, and let's say you're applying 2F and F, the same question which we did. But yeah, the elongation was different. Let's say this is 3F and 2F. T average will be 3F plus 2F by 2. Be careful, huh? If both are pulling, tension will increase. But if someone is pulling and someone is pushing from the back, then in this case, the T average will be 2F minus F by 2. It works only for, don't use it for energy. Because energy is a T square function.
Sir, I think the dividing by 3 factorial works.
हाँ ठीक है ना, अभी कितना फॉर्मुलास बनाएंगे ऐसा. Claim this is just a small shortcut because CET में you get questions of this. They'll give 2F and F and you integration is a waste of time when you're doing CET. Energy they won't touch that. So CET or bits, they do ask, even at a mains level, there are questions like this. Maybe not all. Out of 25, there are 7 to 8 questions which are coming of this level. Saves you time. If you see this year also, now your seniors, most of them have finished their physics and chemistry paper in 1 hour 10 minutes. And then they spent almost 1.5 hours more, like more than that on max. Because once you cross 180 total score, what decides your thing is max only. So we have a rod here hanging. Mass M, length L, area Y, gravity is there. Find a ratio of energy stored in the upper half and the lower half. Find the ratio of elongation and energy stored. Two different equations, huh? In upper and the lower half. What is the elongation in the upper half by the lower half? Find the energy in the upper half by lower half. Again, tension keeps changing in the rod. Let's get this another standard question. So the rod stretches because of its own weight. Nere area. How can it be same? Tension in the upper half is more than lower half. इतना तो clear था. So shouldn't the upper part stretch more than the lower half? Hmm. Be careful, na. It's okay to get a wrong answer. Just don't get blunders. By looking at the question, you can guess the upper half will be more than lower half. So the ratio is greater than 1. इतना तो पता है. So any option less than 1, I would eliminate it. So if it is a mains exam, you will eliminate at least 2 options. If it is a CET dumb exam, sometimes you'll get 3 options which can eliminate. होता है rarely. There was one exam, I think I told you, na, when I was writing my CET exam long back 2006, mein, there is a question in max. Big question. I didn't even read what the question. The question was something like integral x square, blah, 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 blah. Something was there. The final question was find mod x. Options are -1, -2, -3, and 1. क्या करो? And luckily, na, I have a habit. When I read a question, first time I don't read properly. I skip the lines and I just read on the surface. Then I see what they're asking. Then I look at the options. Then I again go back to the questions because now I have a context. But luckily, when I read this question, the moment I saw mod x and I saw post number, I said I don't even know what the hell is the question. I just marked it and went ahead. That was a CET question. So yeah, if you're lucky, sometimes it happens. That looks right, Samyak. Right, sir. Get the energy part also. First, you have to find the tension, everyone. Step 1, find the tension. Step 2, put it in the formula and you're done. There's nothing there. That's what I keep saying. Nay, Rudransh. That is wrong. If you know how to find tension, your problem is over. There's nothing there. Let's find the tension. So the tension in the rod is because of the weight which is hanging below you. So at a distance x from the bottom, take a thin slice dx. So at this position, the tension T will be due to the weight of the rod hanging below this. So tension T will be weight of the rod up to x. Weight of the rod below the dx. How much is that? That would be total mass of the rod m by Lx into g. बस हो गया इतना ही था. What do you want to find? Elongation? What is the formula for elongation? Integral T dx by Ay. You want to find for the upper half by the lower half. So E upper by E lower ratio. Tension is mgx by L dx by Ay. The only thing that will change is the limits. For the upper half, limits will go from L by 2 to L. For the lower half, the limits will go from 0 to L by 2. mgx dx by Ay. mg, everything will cancel. You'll end up with x square by 2. Limits L to L by 2 by x square by 2. Limits will go from 0 to L by 2. This comes to be 3:1. Right, हो गया. Right, Arya. Right, Samyak. Get this energy part, everyone. Energy भी same करना था. If you look at the energy का formula, half into stress square. Stress is tension by area whole square by y into ADX. So if you see everything cancels off, energy in the upper, you can see half will cancel, A will cancel, Y will cancel. You'll actually left out with x square dx L by 2 to L by integral x square dx. This is what I'm saying. This is how you can skip steps in the exam. There's no need to put each and everything. You can see and understand everything else will constant cancel out. 7:1. Right, Arya. Right, Utsav. Right, Shihari. First part is right. Please have a look at this. Again, if you see, I'm just using the same two formulas. Get the tension, put it in the formula, you'll get whatever you want. Any doubts on this? Please ask. टोटल वाला फॉर्मूला एंड सब्ट्रैक्ट वो भी कर सकते हो, बट ठीक है. ऑल गॉट दिस. नेक्स्ट वन. This is an important one. You will see this 3 times, including elasticity. Should definitely remember this. Because if this comes in the exam, it will come in the mains exam. It has come multiple times. You won't have time to derive in the exam. This is a truncated cone. So we have a, basically it's like a cone. Someone has cut off this piece. So it's called truncated cone. This radius is B. This radius is A. This is the length of the rod is L. Y is the Young's modulus. And the length is much, much greater than B minus A. So technically, if I actually draw this picture, you will still think it is a cylinder only. The difference is so small, it's like this. So this thickness, this gap is very, very small compared to the length. We will see why is that later on. Now you started pulling this thing with a force F, and you started pulling this with force F. You're pulling with force F on both the sides. Find the elongation. So here tension is constant, but area is changing. And you should definitely mug up the result. Easy to remember though. Take a break. Come back by 9:40. We'll continue after this. Come back in 5 minutes. Go get away from the screen for 2-3 minutes. Then you can do these questions. Yeah, start off. Chill, let's get this thing. A truncated cone. Now, one thing if you notice in this problem, no matter where you cut, the tension is always same. So in this problem, the tension is same everywhere, but area is changing everywhere. So still have to integrate. Let's see. Exact same problem, we'll again encounter heat transfer and current electricity. That time we will skip the integration. We're going to use the result directly. But now we are going to do.
Sir, is A also like very large?
B minus A is very small, बस.
Okay, sir.
इससे कुछ फर्क नहीं पड़ेगा. How do we choose an element? So let me help you. I'll show you one, one, one. You try to do that step by step. So what was the problem here? The area was changing, right? Again, I'm exaggerating the figure. So the first part is we need to find that radius somehow. How? In terms of x. So let's say this is x is equal to 0. This is x is equal to L. So somewhere here at a distance x, the radius will be r. Can you find that r in terms of x? Let's start from there. It's a math problem. Huh? This is not physics now. Find r in terms of x. This height is b. This height is a. The horizontal length is L. Find the radius of the thing in terms of x. Let's start from there. Try. I'll give you a minute for that. Then I'll show you if you didn't get it. So at a distance x, we are planning to take a thin slice. I want the radius of that. And others, do keep your cams on. Advai, Devanshi, Ishwan, Ovia, cams on, Shaunak. Let's see. Now, there are one or two ways to do this. नहीं रे समय कितना complex नहीं आएगा. You'll get a very beautiful answer. uh, right, Srihari. Got the radius. Right, Aditi. You want the final answer. Now, one thing you can say, this function is linear, and then you can say r is equal to x plus b, but there's a better way. Assume this point is your origin. Then this point ka coordinates will be 0, comma a. Then this point ka coordinates will be x, comma r. This point ka coordinates will be x, comma 0. And this point ka coordinates will be L, comma 0. This point ka coordinates will be L, comma b. So if you actually see that, a straight line, all these 3 points are on a line. 0, comma a. So what you have done here, you have taken a thin sheet like this. This is x, comma r, and this is L, comma b. So if there are 3 points on a straight line, the slope must be same. So the slope of the line will be b minus a by L, r minus a by x. Therefore, r is equal to a into x into b minus a by L. Clear with that? You can actually use the equation of a straight line and finish it off. So from here we'll get dr. If you differentiate on both sides, it will be 0. This will be dx into b minus a by L. So we get dx will be L into b minus a into dr. This is the relation between dx and dr. And be careful, dx is the horizontal length, dr is the vertical thing. That means every time you walk dx distance, radius will change by dr. Is this thing clear, everyone? That is the first part. We found r in terms of x. Yeah, not that one. Now, coming to the question. So at a distance x, we have taken a thin slice of dx and radius r. So dE, the elongation in this small piece, will be again same story, tension dx by ay. The formula is still valid. The tension will be same, T is equal to F, because you're applying F and F on both the sides. Dx will be dx only. Area will be pi r square, and this will be y. But now if you see here, integration where there's a dx here and there's an r here, you cannot integrate this directly, but I already know what is dx. Dx is L by b minus a dr. Take this and dump it here. F is constant, F by pi y integral dx will be dr L by b minus a by r square. So I have converted from x to r. And what is r ka limits? R ka limits, r is going from a to b. This is FL by pi y, or you can keep everything in x and integrate. That also works, but it goes little lengthy. 1 by b minus a, dr by r square ka integral is minus 1 by r. Limits will go from b to a. FL by pi y b minus a. This will be 1 by b minus 1 by a. That will be b minus a will cancel. You end up with FL by pi a b into y. Check. Please have a look at this. First I got r in terms of x. Then I got dr and dx ka relation. Then the same story. I took a small piece at a distance x, dx thickness, r is the radius. The formula is tension length by area y. Area is pi r square. You cannot integrate dx and r square there. It looks like an area of my lips. So I converted dx into dr, and then integration becomes quite easy. I tried this by converting r into x. That integration goes really messed up. So for this problem, right, you can by heart the result. The elongation is FL by pi AB. So the area comes as if, it is a geometric mean. The radius, effective radius comes as a geometric mean A and B ka. It comes like that. Again, this is valid because y is constant and tension is constant. If you mess up y is equal to y naught x, you're gone. This will not work. You have to integrate the whole thing again. But you know how to integrate. You know the process now. But definitely mug up the result. You won't have time to derive in the exam. So whenever you see this question, replace area with pi AB, you'll get the answer in the current electricity and every other chapter. Yeah.
Sir, like we get the area of ellipse in the denominator. Is there like an intuitive way to think we can replace the different areas by an effective area of ellipse?
No idea. मैंने कभी इतना सोचा नहीं mathematically. If you figure out, let me know.
Okay, sir.
Because once you start thinking like that, then every question you will try to figure out a way if there is something. बहुत time consuming है. मतलब exam में you won't have so much time to think about a new shortcut. Just focus on solving and get the damn answer. This is something I keep telling you. In the exam, your only purpose is to solve and get marks. After the exam, your only purpose is to learn and try new things. So yeah, never thought about it, but mathematically, if you can do something, let me know. Ask your maths teacher or you figure it out. I'm
Okay,
not a
sir.
maths person. Clear with this? Any doubts on the derivation? Please ask me. Again, if you see all the integrations are x power n ka integrations, we are not doing any out of the world big integrations. And in physics, the biggest problem is not the integration, but getting the problem into that integral form. All clear with this? Clear now, sir? Great. Next one. Now, this is again simple. Means may you get these kind of models. What if you joined two different rods? Young's model is y1, length l1, area. Young's model is y2, length l2, same area. The second thing we have two rods. Young's model is y1, area a1. Young's model is y2, area a2. They have same length. Basically, they're like in parallel and series type. Find y equivalent in both the cases. Meaning, if you're replacing these two rods with a single rod, what should be the y equivalent for that rod? And this equivalent stuff will come a lot. So you want to replace these two rods with one single rod. So that rod and these two rods, ka elongation must be same for the same force. So what should be the y of that rod?
So the B part in series or parallel?
Oh, parallel है ना, same length. So
Okay.
these equivalent things, right? It will come in elasticity. It will come later on in thermal expansion. It will come in current electricity, equivalent resistivity. They can ask you all this kind of stuff. So I'll show you one thing. So this is what you do. You want to replace this with one single rod. So y equivalent, the length is L1 plus L2. So be careful. Most people mess up that. And let's say elongation in this rod is E1, elongation is E2. So you're applying the same force. That is the meaning of it. So this elongation will be E1 plus E2. So yeah, so what is the formula for elongation? We know elongation ka formula is tension length by AY. So E will be tension, length is L1 plus L2 by A, Y equivalent. Now be careful, in both the cases the tension will be same because you're applying the same force. And what is E1? E1 is a tension, length is L1 by A, Y1. Tension, length L2 by A, Y2. There. So 1 by Y equivalent will be L1 plus L2 Y equivalent is L1 by Y1 plus L2 by Y2. That is how you find Y equivalent. So the total elongation in this rod must be E1 plus E2. So E will be this and E1 will be this and E2 will be this. So when you're in series, you have same tension. All got this? How to take this? That's how you get Y equivalent. Now in the other case, when they're in parallel, they have same elongation. So basically, generally what happens, right? You keep them between two walls or two supports. So they're something like this. So when you're pulling them or stretching them, they'll have same elongation. So elongation is same. So in this rod, if you have tension T1, and in this rod you have tension T2, and you want to replace this with one single rod whose area will be A1 plus A2. And the tension will be T1 plus T2. So tension adds up. Again, same thing. So formula for tension will be YA by L into E. So tension will be pi equivalent. Area will be A1 plus A2 by length. Elongation is same. T1 will be Y1, A1 by L. Elongation is same. This is Y2, A2 by L. Elongation is same. Y equivalent will be Y1, A1 plus Y2, A2 by A1 plus A2. Yeah. Yeah, you can also do that actually. You can relate them to like a spring and get an equivalent spring and then relate it to works. That also works. Clear what we did? So when you pull this thing, you get different tensions, but they have same elongation and same length. When you keep them in the same line, you get same tension. That is the idea there. But pretty good mains level questions. The equivalent thing. All clear with this? Now in this chapter, there is one formula, the experiment also. We call it Searle's apparatus. Experiment is quite easy, but the terminology is important. Especially advanced when they'll ask you in experiments, you get this kind of questions in errors. This is an experiment to find Young's modulus. The total physics, I think you have around 12, 10 to 14 experiments, depending on how we take it. And you should know all those experiments. Advanced, they have a good weightage. So this is an experiment to find Young's modulus. Luckily, this you won't find in the lab because to do this experiment, you need almost 2 floors ka height. And your school labs are not equipped to do this. So how does the setup look like? So first, let's try to understand the setup and then I'll explain you how it works. This still looks beautiful. The actual setup looks pretty tall, almost 2 meters long and everything. So let's look at the whole picture. I'll draw a rough picture. From there, let's try to understand. So look at the picture I'm drawing on the right-hand side. So we have a wire attached with a weight of mass m. So this is called dead weight. So basically, it is kept to keep the wire straight. And this is your reference wire. So this wire is fixed. Now let's say you brought some copper wire or a steel wire and you want to study the Young's modulus of the wire. So you bring that wire and you keep it parallel to this. Maybe I'll use another color, black. This is your experimental wire, the wire on which you're trying to find. Now on this wire, what you do, you attach some weights. So we have weights which can keep varying. So this is tension. This is mg. This is T is equal to mg, which is variable. So you can add and remove weights to change the tension. There, that is this one, is slotted weights. It is written here. That is this one. So by adding and removing weights, you can change that. This left side is a dead load. This is the dead weight, which keeps the wire straight. Auxiliary wire is the reference wire, experimental wire. So this is where you connect the wire. Picture it is looking small. In reality, this wire is almost 2 meters long, minimum. Because the elongation is so small, you get it in millimeters. You need to take a long wire to get an appreciable elongation. So far, the thing is clear. Now, what happens when you add the weight, the wire will stretch. So how do we figure out how much the wire stretched? So we keep something called a spirit bubble. So we have a thing like this. You have an air bubble inside, which is filled with a spirit. Normally, if you see, people in construction use this to make sure it is flat. This is called a spirit bubble. So basically, you take a glass pipe, fill it with spirit ka liquid, and leave a small air bubble. The idea is this. This thing now will look like this. If you ever see this, there. This is how the thing looks like. This is the spirit bubble. You can see in the middle, there's an air bubble. How does this work? I think even your app, phone, iPhone and your Samsung phone, whatever phone, they have an app like the spirit thing. If you keep this on the floor, it will be exactly in the center if it is flat. So if the rod is exactly horizontal, then the bubble will be exactly in the center. That is how you know whether the surface is flat or it has some tilt. Suppose if the surface is tilted, the bubble will go up. Then we know the right side is little higher. Suppose if the left side is higher, then the bubble will be here. Is this clear? So if the bubble is in the center, we know both the wires are exactly same length. It's not why you want to drink this spirit, Ray? Don't drink. People now. Out of all the things, that is the doubt you have. Don't drink spirit. This is not a good thing. This is mostly people use methyl alcohol, which is poisonous. You become blind. Kabhi suna wo word? In some normally what happens, right? For industries, they produce alcohol. Ethyl alcohol they produce for industries. This is very cheap, and this is manufactured completely chemically. But if you see the regular alcohol, right, which they actually make it from fermentation. They take these rice grains or all that stuff, ferment and get ethyl alcohol. But chemically speaking, right, if you produce ethyl alcohol from petrol or if you produce ethyl alcohol from fermentation, you can't tell the difference. You can't tell the difference. Both are one and the same. So this factory is right. They produce a lot of ethyl alcohol in bulk, and this is very very cheap compared to the thing which they produce. But then what happens? Some of these employees, right? They steal this ethyl alcohol while traveling and then sell it off for cheap. And these drunkards who are there, na, it nowadays it has stopped a lot. But when I was in school ka time, na, around 2000s, used to happen a lot. And now, because people are stealing this alcohol and selling, na, the government, what they used to do, they used to mix methyl alcohol into that. Now, when you add methyl alcohol, which is CH3OH, that does not affect for the industries. Industries have no problem. But when humans drink methyl alcohol, you become blind. You become blind, you get poisoned. Now, in order to stop this leakage, they added methyl alcohol into it. People, without realizing, they started stealing this petrol, this alcohol tankers, and started looting them and started selling it off. People literally used to die. Huh? We used to get a newspaper like literally every day for almost 4 or 5 months. People didn't realize only they're mixing methyl alcohol. Then the government had to come out and say, boss, they're mixing poison in that. So stop bloody, stealing that and drinking. So don't drink spirit. Getting it? That was one. It's an alcohol poisoning. Something like this recently happened. Recently, 7, 8 years back, it happened. Government, na, it gives subsidy to farmers to, for urea. Urea, right? They use it for fertilizers. Okay? So every farmer gets around 2 bags of urea for very cheap cost. If the urea cost is 100 rupees, normally a bag is around 400 or something, the government gives them for 40 rupees. It is subsidized. Getting it? And I think every month or something, they get 2 to 3 bags, something like that. There's a limit. Now, these farmers, what they started doing, everyone used to go, you are a farmer. Now, let's say in your family you are there. You are a farmer. Your wife is a farmer. Your kid is a farmer. So every person used to get 2 to 3 bags. Everyone is a farmer. Matlab, you just register yourself, everyone is a farmer and bloody everyone get 2 bags. And they used to get these urea bags very cheap. And they used to sell these urea bags to this industrial companies which produce ammonia. Now, that same industry, if it goes to the government and tries to buy urea to produce ammonia, the government will sell them for 400 rupees. These people used to pay the farmers 200 rupees and used to get the bags. Farmer is happy. I got the bag for 40. I'm selling for 100 for 200 rupees. The factory is happy. I'm getting for 50% cost. The factory started looting literally. The government ka subsidy, right? They started stealing like this. Everyone used to become a farmer in the village. Actual farmers 1,000, but when they come for urea distribution, there are 10,000 farmers. Right? So, मतलब school holiday उस दिन क्यों मैं farmer बन रहा हूँ आज? Then what the government did? Now this is what I'm saying. You have to be smart. Then what the government did? This urea, whichever they're giving it to the farmer, they started coating it with neem oil. They started mixing neem oil into the urea. And what did the government say? The government didn't say anything about stealing and all. If you say that, people will get angry, right? You can't call a thief a thief. It feels bad. So what they did, they started adding neem oil into the urea. So they're coating urea with neem oil. And they give a simple explanation. By adding neem oil to the urea, right, it will help you protect from the insects and the farmland becomes it is more organic. Done discussion, simple thing. And when companies actually started using this neem oil in producing of urea, their boilers which they're boiling, they started getting damaged. That neem oil is damaging their equipment in the factory. So you can't use this neem coated urea anymore to produce ammonia. Done. Stopped. That's it. Matlab, literally the subsidy, right? I think they used to spend every year something like 4,000, 5,000 crores of rupees on the subsidy. It dropped to around 300 crores. 1/10 of the cost. Just by adding some neem oil, which costs you around 10 rupees per liter or something. There. So if you're smart enough, you can do all this shit. So depends. That's a little bit of chemistry. So that is how you use chemistry to steal and do stuff. So it works. Anyways, but all clear with the spirit bubble, how it works? Great. Now, how does this experiment work? Let me show this picture again. So now you start adding the weight on the right hand side. Now, once you start adding the weight on the right hand side, you will observe the wire on the right side will stretch. Now, because the wire started stretching, this spirit bubble will actually start becoming inclined, and the bubble comes here. And that is how you know the wire got stretched. Clear? There. That is how you know the wire got stretched. Now, if you observe the thing here clearly, can you see here? There is a screw here. Basically, this is a screw gauze. This is a speriometer ka screw. This screw here, they start rotating this. The screw is rotated. When you rotate the screw goes up. So there is a screw here which is supporting this thing, and you start rotating the screw. So when you rotate the screw, this thing goes up. This is your delta L, or your elongation. So you have to keep rotating the screw till the spirit bubble becomes again horizontal. Screw is rotated till the spirit level becomes horizontal. So can I make this argument? The elongation in the wire is distance moved by the screw. Do you agree with that statement? Whatever distance the screw will push it up, isn't, and when it becomes flat, isn't that the elongation in the wire? If the wire has come down by 2 millimeters, you have to rotate the screw by 2 millimeters in order to push it back to the horizontal level. This is how you find the elongation in the wire. So elongation in the wire is nothing but the distance moved by the screw. That you can get it done using a screw gauze. We'll see that later on. So every time you rotate one complete revolution, the screw will move 1 millimeter. So you're done. You got everything in the formula. What is the formula? Young's modulus is equal to tension. You know the tension from the weight, length of the wire that you can measure initially, area of cross section that also you can measure, and elongation. Put it in the formula, you get the answer. The experiment is pretty straightforward. Is the experiment clear, everyone? Again, what is the experiment? Listen, we have a reference wire. You bring your experimental wire, you keep adding weight. When you keep adding weight, the wire will start stretching. When the wire starts stretching, the spirit bubble, which is horizontal, starts becoming like this. Then you have a screw at the bottom here, which when you rotate the screw, it will push the spirit bubble up. Again, it becomes flat. So the distance moved by the screw will be the elongation. I know the tension, elongation, area, length. Put everything in the formula, you get your Young's modulus. Any doubts on the experiment? All clear with this? So experiment is easy, but remember the word Searle's apparatus, because exam mein question will come like this. It has come in advance. Question came something like this. In a Searle's apparatus, a screw gauze is used, which had a pitch of so and so. That is all based on screw gauze. We'll see later on. When it is rotated by 1.5 revolutions, the spirit bubble became horizontal. The people who don't know the experiment, right, they'll not understand what they're talking in the question. But if you understand, it is pretty straightforward. Yeah, no, it is not to move the wire, Srihari. It is to move that spirit bubble up. All clear with this? That is one. The next thing, there is a small graph here, which is again quite important theoretically. So listen carefully. Stress strain curve. So when you take this wire and when you keep adding weight, we observe it doesn't behave the same way throughout. It starts actually getting messed up. So again, don't really think too much. Huh? Stress is nothing but force by area. Strain is nothing but change in length by length. So indirectly, this is F versus X graph. This is a graph between force and elongation. So let's see the graph here. So when you keep adding weight here, consider a wire hanging from the ceiling. As the weight increases, weight is added continuously, increasing the tension. So we are studying how does the stress and the strain curve vary. So the graph, right, looks like this. So first part, the graph will look like a straight line, O to A. So A is called the proportional limit. So basically in the region OA, so when the wire is going from O to A, stress is proportional to strain. This is what you have studied so far. Basically, it behaves like a proper spring. Hooke's law is valid. So in the region OA, forces are linear and conservative in nature, meaning there will be no dissipation of energy. If you remove the force, it will come back to the natural length. There are no loss of energy. Forces are linear and conservative. Then, if you keep on adding weight, then the second part of the graph, now it is not a straight line anymore. We get something called E. E is called elastic limit. So when you go from A to E, again, remember when I say you're going from A to E means you're increasing, more and more weight. So stress is increasing. In A to E, stress is not proportional to strain. The function is not linear anymore. You can't use it as a spring. There is one more thing I forgot to add here. So the slope of OA, the slope of the line OA is nothing but stress by strain, which is actually Young's modulus. So in the stress strain curve, the slope of the line gives you the Young's modulus. Then have a look at this. That will write in the next page. So now once you exceed point A, the forces become not linear anymore. E is called elastic limit. Stress is not proportional to strain. So you don't want to use this region to make springs because spring F is equal to Kx. But in AE, the forces are still conservative, but not linear. And there have been statement questions on this. In which region forces are conservative? In which region forces are linear? Forces are conservative, meaning you still don't lose energy, but not linear anymore. So the meaning of this is if you remove the external force, that is, if F external is removed, you come back to the natural length. But if you exceed E, that means if you keep adding more weight, then your graph will even go higher. You reach something called U. U is called ultimate strength. So in this region EU, right, if F external is removed, so once you cross E, and after that, if you try to remove the force, you won't come back to the natural length. There is a permanent deformation. Did you ever do this? वो पेन में वो spring होता है ना? Did you see that? Pen में that thin spring is there. If you take that spring and if you stretch it a little, it is fine. But if you stretch it too much, what will happen? It will does not go back to the initial length, isn't it? Did you ever do that? If you take a chota spring and if you pull it too much, it doesn't behave like a spring anymore, right? If F external is removed, it doesn't go back to the natural length. So basically, you have permanently damaged the structure inside, the molecules and whatever. The deformation is permanent. There is a permanent deformation. The wire actually got stretched. So that means if you leave it somewhere here between E to U, if F external is removed, it comes to this point here, O dash. Look at this green line up. When you're here, the stress is zero, but the strain is not zero, means you got permanently deformed. So this OO dash is your permanent deformation. That is how you show in a graph permanent deformation. Means if you reach between EU and then if you try to come back, you won't come back in the same way. You'll actually come back and stop here in the graph. This is a permanent deformation. If you take a chota spring and stretch it too much, that's what will happen. So in this region, forces are not linear, forces are not conservative. You actually start dissipating. This is the region where it starts becoming hot. Forces are not linear and not conservative.
So in this region, like more energy is converted into kinetic and then it's lost, right? And less is going into
Hmm,
potential.
you
Can we
can
say
say
that?
that. You
Okay.
can say that. Now, if you exceed U, मतलब ultimate strength के बाद if you keep adding more weight, now things will start going bad. This material will start dropping. Now that's a very unusual behavior there because think about it. Normally, when you increase the stress, can you see? When the stress is increasing, the strain is also increasing, meaning X and Y both are increasing. For the first time, you will notice after U, the stress is decreasing. Matlab you're applying less and less force, but the material is elongating more and more. Do you remember this Tom and Jerry में होता था? The Tom is hanging on a rope, right? And the Jerry comes and starts cutting it. The rope becomes like this. It becomes like a thin strand. And that thing stretches, 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 and then breaks. Do you remember seeing something like that? Right? So patience, Srihari, patience. So once you cross this point here, we reach a point B here. B is called the breaking point. That means once you cross this point, after you, the bonds are broken so badly, right? There is no bonding between them. The molecules are getting separated now. You're getting it? So there's nothing to stop between them. So after you, the material behaves like a plastic body. Again, be careful. Plastic matlab, not your stool ka plastic. Do you remember what is plastic materials? हमने starting में define किया था. What is a plastic body? These do not generate internal restoring forces. मतलब चपाती का dough जैसा. The material got so messed up. It's like your chapati ka dough. Did you ever take a chapati ka dough and hold it? What happens? It stretches on its own, right? It just keeps on stretching. The material behaves like a plastic body. Think of chapati down. That is a good example. Because when I say plastic, people think about a plastic chair. That is, even when the stress decreases, that means even if you try to decrease the force, you're gone. Matlab, it is a breaking limit. Like you have gone to such an extent. Even after trying to reduce the force, nothing is going to change. Happens, na? You have a fight with your friend and you say so many bad things about your friend. You scold him so much. Done. After that, your friend does not want to come back to you again or talk to you anymore, even if you apologize. You have crossed the line. Something like that. Right? So even if stress decreases, strain increases. So technically, if you decrease the force, elongation should decrease, but like no, you're gone. That's why it behaves like a plastic material and finally breaks. So once you cross U, you're done with the material basically. Not a good sign. But this thing gives you an important thing. That means if you cross U and if you can reach till U, right, the material can be made into thin wires. So this length E to B is proportional, U to B is proportional to ductility. This is the ability to make into thin wires. Technically speaking, right, it should have been E to U, but in NCRT it is given U to B. So we will stick with that NCRT thing. Because once you cross U, technically the wire goes off and breaks, but maybe if you decrease the force a lot, it goes off. But anyway, so this is the ability to make into thin wires. So that's your ductility there. So there are two important points here. Once you cross this point, the material behaves like plastic, and the material, right, will have more ductility. So just to give an example, the questions will be on this. So that is the whole story about this graph. Proportional limit, elastic limit, ultimate strength, and this thing. There na YouTube. Srihari.
Sir, you are talking about length of curve or the displacement?
It really doesn't matter actually. So I should not say length, but UB bolo bas.
Oh,
Bas that UB ka whatever is the distance. So how will they frame questions on this? One way of asking question, they'll give you two graphs and they'll ask you to compare. So this is A, this is E, this is U, and this is B. This is A, this is E, and this is U, and this is B. So this is your material 2, and that is your material 1. So examine they'll ask you like this: which material is good to make springs, and which material is good to make what do you call wires? Which material has a good Young's modulus? If you look at the line slope OA is equal to Young's modulus. So more the Young's modulus, the stronger your spring. So if you take these angles here, theta 2 and theta 1. So this is one question they can ask you. Tan theta 1 is greater than tan theta 2. Compare the Young's modulus. So the material 1 will have more Young's modulus than Y2. Second thing, can you see that UB ka length? It's pretty long for the second one. So the second material is good to make wires. Material 2 is better for wires. Maybe copper. Material 1 is like a glass. It breaks immediately. Means before breaking, it will stretch a lot before breaking. Isn't that good to make wires? You want the wire to stretch a lot before breaking. That is one way they can ask you. And another kind of question they'll ask you is this. They'll give you a hypothetical graph. Like this. O, A, B, and C. And then they'll ask a question like this. In which region the material behaves like a plastic? In which region material behaves like a plastic material? Any doubts on anything on this? Now see, remember the meaning of plastic body. What is the meaning of the plastic body here? Even if the stress decreases, the strain should increase. So in this graph, in which region the stress is decreasing? Look at here, from O to A, stress is increasing. That is, y-axis is increasing. X is also increasing. Fair enough. B to C, both are increasing. Look at A to B. A to B, stress is decreasing, but the strain is increasing. That is how you decide which region is plastic. बस इतना ही करना था. So if you see this region here, A to B, stress decreases, but strain increases. So that is a plastic material. Hypothetical normally, but yeah. That's your plastic region. That is how they can ask theoretical questions on this. Clear with this? हाँ, Arya.
Sir, in the definition you have wrote, even though the stress decreases, the strain
Mm-hmm.
increases. सर ऐसा
Yeah,
भी तो हो सकता है कि स्ट्रेस इंक्रीज हो रहा है और स्ट्रेन भी इंक्रीज हो रहा है पर फिर भी वो प्लास्टिक बिहेवियर दिखा रहा है.
I didn't understand.
सर मतलब इवन दो लिखा है ना तो नॉट नेसेसरी
Even
कि
निकाल
डिक्रीज
देना
होना ही
if.
चाहिए. अच्छा ओके.
If कर लेना अभी मतलब तेरा प्रॉब्लम इवन है तो.
आई मीन आई
Clear with
थॉट
this?
कि इवन दो द स्ट्रेस इज डिक्रीजिंग मतलब डिक्रीज होता है तब इंक्रीज हुआ तो वो फॉर श्योर प्लास्टिक है पर अगर इंक्रीज हो रहा है और स्ट्रेन भी इंक्रीज हो रहा है तो हम बोल नहीं सकते फॉर श्योर.
Okay. ठीक है ना, you're catching the English point. ठीक है. Got this? So if you see, right, so far what we did is all longitudinal stress and longitudinal strain. And this is the major part of the chapter. After this, we have two more things, shearing stress and shearing strain, which will give you a new thing called rigidity modulus. Then we have something called volume stress and volume strain, which will give you bulk modulus. So ऐसा तीन moduluses हैं. Like I told you, there are three different kinds of stresses, longitudinal, shearing, and volume. So we studied longitudinal so far. That is a major one. The other two are small. They won't take much of our time. So next class, when we catch up, we will wrap up the chapter. I think it will take another 1.5 hour. And after that, we'll start off with a new subtopic, like new chapter in thermodynamics, thermal expansion. The next class, we'll start with something new. Okay, we have done almost a decent number of questions, 10 questions. So go through this, right? So I'll see you guys again next Tuesday, same time. We'll continue from here. So any doubts, anything else, please stay back and ask. And do remember there's a test online till tomorrow, so make sure to give it. So any doubts, anything else, please stay back or else you're free to leave.